And here we have arrived at polar functions. Now this is going to be what I call a survey into polar functions, that being we are going to be rapidly falling out of our depth with this one. I'll show you what I mean here in a bit, but we will have either one of two options. We're either going to have a whole bunch of memorization on our plate or a whole bunch of desperate point plotting on our plate. In either event, we're not going to go too terribly deep on this one. But all the same, I want you to see where we're coming from because your author really kind of drops the ball on this one. So here we go. In this video, we're doing two things. First of all, we are going to define a polar function formally. We did it kind of informally there at the end of the last video, right? We kind of stumbled across r equals something in theta, and we're going to kind of formalize that. And then, I'm just going to do a survey on this sort of stuff. I'm going to do a survey on polar functions. I'm just going to graph a whole bunch of them for you rather quickly so you can appreciate just how powerful they are and also appreciate not having to memorize all these things, which, curiously enough, is what your author would wish you to do. So, here we go. Let's see what I mean. Remember, first of all, that if you had y equals something in x, right, some expression entirely in x, if y equaled that expression in x, you could call that a function. We had things like f of x is sine x, g of x is 2 tangent x, h of x is sine squared x plus 2 sine x plus 1. All of these are functions in x, right? The output of the function, we would just make that be the y value of a ordered pair. And so the function being the collection of all those ordered pairs is exactly what we would get whenever we have an equation where one variable, usually the dependent, is entirely dependent on some expression of another. Right? So each of these are expressions of one variable. The x value is the independent variable. The y value is the dependent variable. It's also the function output. And that's how we made functions back in the day. Right, these are some functions we looked at. Actually, these two are functions we looked at earlier. This one is not one I made as graph because I'm not, hurtful like that. But I guess you could. Well, now we're going to do the same for polar systems. R is going to be a function of theta. So theta will be our independent variable. R will be our dependent variable. We'll see what I mean. And this is how we kind of see things going off the rails pretty quick. Here's the function we had last time. R equals 2 cosine theta. So I'm going to make R a function of theta. So every time I put in a value for theta, I get only one value out for R. That is a function in the system we have defined. So, right, 0 goes in, 2 comes out, because that's 2 cosine 0. Pi over 4 goes in, square root of 2 comes out, right? Because the cosine of pi over 4 is root 2 over 2. That doubles to just be square root of 2. R of pi over 2 is 2 cosine pi over 2. 2 times 0 is 0. 3 pi over 4 is negative root 2. And actually, I guess technically I should have been skipping around like this, because this is from 0 to pi over 6 to pi over 4 to pi over 3. Stepping up all the way around the first bit of rotation. So take a moment, make sure all these points are correct, right? 2 comma 0, root 2 comma pi over 4, 0 comma pi over 2. Make sure these are all correct. And then we will look into plotting those. And also while you're looking at it, see if you could also complete this for the other half of the nice values of the unit circle. So go ahead and find r of theta when theta is 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2. All of those in this third and fourth quadrants. Get those points for me as well, and we'll see what we can do about that. Alright, so you got them? Great. Now, take all those points, all those r comma theta values. Now, the sad part is, x comma y, the second coordinate was the dependent variable. Well, now the r coordinate, right, the r value is the first coordinate, which is now the dependent variable. So that kind of flip-flops, but everything else works pretty much the same, right? So this point you would plot as 2 comma 0. So let's see here. That would be, right here. Then the next point is root 3 comma pi over 6. So pi over 6 is square root of 3. That's about here. I don't know what I did. I regret it though. So that would be about here. And then pi over 4, root 2 comma pi over 4. Well, it's pi over 4. And root 2 is about 1.4, so about there. And, actually plot those for me if you would. Pi over 3, that gives an r value of 1, so 1 comma pi over 3. And then you just keep going around plotting all those points, and what you should eventually end up with is a whole bunch of stuff around like this. And then hopefully you'll see that with the points you found, you would also get these down here connecting back up here. Now here's the simple beauty of this, right? As theta continues going up and up and up, this just keeps circling around and around. And that's because cosine is periodic, right? Periodic to pi. So, connecting the dots, we actually get a circle centered at 1, 0 of radius 1, which our commanding knowledge of conic sections would have told us. So, awesome. So 1 down, right? We plotted, oh goodness, I don't even want to count how many points, but we got a graph of a function, which is great. And polar functions actually do have their uses, and they're rather cumbersome. So you're just going to have to kind of take me at my word for that, or see me, or do some digging yourself. They have their uses. And if nothing else, as you'll see here at the end of this video, they are also profoundly gorgeous to look at. This one not so much, right? This one's not that cool, but we'll see some that are cool. So here's another one I want you to stop and think about. What is this graph here? R theta equals theta. So theta goes in, R comes out to be exactly equal to it. Right? This is kind of the logical equivalent of x equal to y. Or I guess technically I should say y equals x, right? So every x value is also my y value. So our standard y equal x guy, our identity function, right, for way back then was just this diagonal line, y equal x. Well, what is it now? What are the values here? Well, 0, 0, pi, pi, pi over 4, pi over 4, right? Every time I have some r value of any number I want, I'm going to rotate by that same amount. So this is our identity function. It's a spiral. That's a function. I don't care how many times it fails the vertical line test, because this isn't polar, right? This isn't rectangular. I don't care. This is polar. So yes, it does fail the vertical line test, but so what? This is a function now. Also, as a curiosity, do you want to know what equivalent rectangular equation that would have to be? It would have to be the same solutions of x squared plus y squared equaling the arctangent of y over x. Of course, that only gets a little bit of it, right? Because arctangent has the restriction. It doesn't go anywhere past negative pi over 2 to pi over 2. So we would also have to include this plus pi. And then this plus 2 pi. And then this plus 3 pi. And just keep going all the way around. And you see the overlap there? Oh, there we go. Yeah, see the overlap? But Mr. Terrell, you exclaim, this doesn't have, this has extra stuff to it. And you're right. The reason for that is a convention where most people, when they're graphing polar functions, and indeed all computer programs pretty much, Desmos included, they start with theta equal to 0, and they count their way up. So that does not account for negative theta. And there we have it, right? That's the other half. So this guy, right, root x squared plus y squared plus arctan y over x plus k pi for all values pi would generate the same function the same graph, r equal theta. And I wish you the absolute best of luck trying to solve this thing. Just the absolute best. I wish you all the best in the world. But this guy, this logical equivalent takes only seconds. And that's fun. That's fun. That's nice. I like that. I like that a lot. So there's our strategy, right? When we got a polar function that we're trying to graph, really our only bet, our only safe, sound, reasonable bet is to plot a bunch of points. So for this guy, we plotted all these points. For this guy, you would have just said, okay, when theta is 0, r is 0. When theta is pi over 6, r is pi over 6. When theta is pi over 4, r is pi over 4. And you just go all the way around as many times as you feel like you need until you've got it. All right. Now then, it's time now to see just how powerful these functions can be. Because these are functions. Whatever you think you see, you are looking at functions. And actually, I've deliberately written the equations over here so that you'll see them. R cosine theta. Yeah, okay. Not that cool. I know. I'm underwhelmed too. What an awful start. R sine theta. Okay, still stupid. It's just up now. Fine. But what happens if I double it? Heyo. R sine 2 theta, and if you feel like it, you can trace this out, recognizing this is going to have period 4 pi, because I'm doubling this, right? So this is going to be all the way around, just like that. Or is it periodic pi? One or the other. Periodic pi, I think. And then here's cosine, right? So I have off-kilter 4-leaf clovers. These are functions, by the way. Cosine 3 theta is a 3-leaved clover, a 3-leaved rose. They call them roses in the math language because reasons, I guess. It doesn't really look like a rose, but for fat enough petals, I guess it would. And this guy, this is a function now. This heart-shaped thing, sometimes referred to as a cardioid because it's a heartoid, is a function now. And you can actually plot this out by just plotting enough points. That's 1 cosine of theta plus pi over 2. And here's your spider graph, right? You can turn these roses into things that actually look like roses. And that's legit. That is a legitimate function. Also, you can see just how far theta goes before the Desmos just gives out. You see how some of these are thicker than others? That's because they're actually very, very close lines. And Desmos only has a finite number of points it can plot before it gives up, and you can actually showcase that with very particular polar functions. So here's another cardioid that's kind of collapsed in on itself. I forget if they call these limasones or not. Your author just loves having you memorize all these things, but you can just plot it out. Just plot it out. You can plot rectangular things here. I have solved y equal x squared in terms of r and theta, and so dividing through, solving for r, you actually get a parabola. So you can get all of your standard algebra side functions as well. And then you get some pretty weird stuff too. You can get a cell halfway through division. I think that's called a lemniscate. You can get, oh goodness, a cardioid that's really having a bad day. I forget the name of that. This is pretty though. These are all functions. These are all functions. And I find that truly fascinating, truly fantastic, that thing right there is actually a function. And we know how to define it. We've written it out accordingly. And we know how to plot it. Just by very carefully moving up with theta and plotting all the points we get, we would end up here. And that's fantastic. This is a truly beautiful thing. And for whatever reason, your author wants you to memorize all these things, what they look like and all that. And I'm just going to say no. That's a hard no on my part. All I want us to do with these functions is if we need to graph out an equation, if we need to graph out a polar equation, let's turn it into a polar function. And then move through theta, plot some points, and connect the dots as best we can. Any more than that, and we are out of our depth, and we would need graphing software. All right, that's it for this. Have a good one.